Hello and welcome to the first session of our second edition of the Aerospace workshop by SimScale featuring Auravia. Yes, I'm very glad to see so many people participating in our first session today. And actually, before we start to dive into the really interesting world of engineering simulation and aerospace design, I would like to make sure that the audio is working fine for you. So guys, in the software we are using, GoToWebinar, you will find a button which is called Raise Your Hand button. In the case you can hear me loud and clearly, please click this button so I will know everything is working fine. Great, I already see some hands raised, very good, perfect. Okay, just in the case during this webinar something should happen, for example the audio connection drops, you can leave and re-enter the webinar. Or if you cannot solve it this way, you can also use our toll-free audio service numbers, which you will find on this slide. So in the case, for example, you live in Switzerland and you would like to join the session via phone, you can just dial this toll-free number, enter this access code 195.264.705, and you will be able to listen to the audio stream via your phone. Great, okay, then let's dive into it. And today is our first session, which will be about the optimization of a wing of an aircraft airfoil. And let's take a quick look at the agenda. First of all, I would like just to introduce you to the concept of this workshop series. We have a lot of new participants who have not joined the first edition of the Aerospace workshop series, so I think it makes definitely sense just to talk a little bit about how this workshop will work exactly. After that, you will get a very short and crisp introduction to the fundamentals of simulation. And after that, we will start to talk about aircraft wings and how we can optimize them using fluid flow simulations. Finally, I will present a homework assignment to you, and after that, we have time for your questions. Okay, and just in the case, during this webinar, if you have a question or something like that, we have also a window, a chat window for questions. Just type your question into this question window, and I will try to answer the question as soon as I can during this session. Okay, great. Then let's start and talk a little bit about our today's webinar. And first of all, I would like to introduce myself. My name is Milad. I'm working at SimScale as an academic program manager, so I'm responsible for all our activities with students, research institutions, and let's say other people related to academic. And as part of this role, I'm also organizing and delivering the workshop series we're offering for you. And maybe just first of all to make it clear, the aim of this workshop series to share interesting insights about engineering fundamentals with people, students who are really interested in aerospace engineering. We will therefore keep everything very hands-on and really focus on how to create the simulation and what kind of fundamental knowledge do we need to be able to perform the simulations. This also means that we cannot focus too much about simulation theory. So in the case you're very interested in this deep fundamentals like the Navier-Stokes equations or some other stuff like that, we cannot cover it so much. But as you know, you can qualify for a free professional training, and there we will talk more about that. And yes, this training is really focused on practical applications. And finally, a lot of people asked us why we are offering these workshops and webinars. The reason is very simple. Everyone in SimScale truly believes in the idea of engineering simulation. Therefore, one of our aims is to allow every engineer or future engineer in the world to be able to use simulation. And for sure, we are very interested in product feedback. So if there is something you would like or you think we should add to our platform, or is this something you like very much, what you want to say us, or just let us know. You can reach out to me on email, using the forum, and on many other ways. And finally, how does this workshop series work? Basically, we try to combine both maximum flexibility for the participants, and also to have, let's say, a closed curriculum and make sure that everybody will learn something here. Therefore, we will have 3 one-hour online sessions, which will be delivered as a webinar. And in this webinar, we will talk about some fundamentals you should know. You can ask questions, and I will show you a dedicated application of simulation engineering with SimScale. And after that, you have 1 week time to submit an optional homework assignment, which is about creating a simulation on your own. For this, we will provide you with free access to the tools you need, as well as a tutorial, but about that we will talk later. And you can share this homework using a form on simscale.com. And if you submit all 3 homeworks, you will get a free professional training with a value of €500 and a certificate of completion. Since Brandon already asked a question which I'm asked a lot of times, let's quickly talk about our FAQs. So first of all, yes, we will record this workshop. So like every other workshop, it will be recorded. And after that, we will provide you with a recording on our YouTube channel. And I will send you a link, I think, tomorrow around lunchtime, including the link to the recording and other resources you need. And in general, please don't start to simulate yourself during the workshop. You can watch the recording whenever you want, and you will have a lot of time to do the simulation. You should really try to focus on the presentation and ask questions. Everywhere, if you're confused, just ask a question. And maybe something also is very important, in the case you should have trouble setting up your homework simulation, we are offering you free support. I will show you how you can get access to the support later on. And if you want to learn, for example, about topics which are not covered here, we have a lot of other workshops, webinars, and learning resources you can access for free. Okay, then let's start. First of all, I would like to talk with you about the fundamentals of simulation. And this can be, let's say, very boring, but let's try to make it very hands-on and crisp. And now let's go a step back. And first of all, what is simulation? To put it in a nutshell, engineering simulation is summarizing technologies which allows you to perform or to replace physical experiment by virtual experiments using a computer and some software which is able to model your physical problem. And engineering simulation was in the end invented like 70 years ago, and became from time to time more and more important for different industry. And first, or early adopters, for example, were the aerospace industry. And the reason is quite easy. Let's take a look at the standard way products are designed without simulation. Just imagine, I think that's a very good example, even it's maybe not 100% related to aerospace. Just imagine you work at a supplier for Airbus, and you have to design a new valve for the hydraulics of an airplane. And usually you will get a list of requirements from your supervisor or from the client, saying, for example, when we talk about the valve, we need this diameter for the valve, we want to have this mass flow through the valve, and we want to have maybe maximum this pressure drop. And basically, the main function of the valve, opening and closing a hydraulic circuit, is delivered by a valve body, which is inside this outer shape, this housing of the valve, and which can open and close the cross-section. But if you want to design this valve, first of all, in the conventional design process, you have to design and construct everything. So the valve and the body and the valve housing, but also every little screw you can see. If you just take a look here, I mean, basically, this and a part inside you cannot see is the main function of the valve. But then you also need all screws, the sealings, the cables, and after you have designed the complete product, and which takes a lot of time and costs of money, then you can manufacture a physical prototype, test it, and by 99% you will have to change the design several times because the current one will not fulfill your requirements. And that is really a very costly and time-consuming design process, which is not very smart. Using simulation allows you a completely different way of designing products, because let's get back to our example. Instead of designing the whole valve in your CAD system, including all the sealings, the screws, you will just make a very rough design study first, and just use simulation to optimize the fluid flow through this valve. And once you say, oh, that looks good, then you can start to finish everything. And finally, at a very late stage, design a first prototype, validate your simulation, and by a very high chance that you can directly after that start to produce and ship your product. And that's basically the reason why we need simulation, or why simulation can improve really the the working processes for 100 million engineers in the world. And you may ask yourself, oh, sounds like a very good deal, but why are not a lot of companies using simulation? Why is it not a standard tool for everyone? And the reason is that simulation traditional simulation tools were very cost intensive. You needed dedicated software licenses, a very performant computing system, and a lot of knowledge to use these tools. And basically, and this is the only time I will talk about our company, what SimScale, we are a startup company from Munich, and we've developed the first web-based simulation system, which means SimScale is a full 3D simulation tool running in your web browser. You don't need to install any software, download any software, and you don't need a license. Everything will be working in the cloud. And SimScale is even more than that. SimScale is a simulation ecosystem because we are combining functionality, which means our end-to-end CAE platform in a web browser together with content and people. That means SimScale is a place where you can find hundreds and thousands of high-quality public accessible simulation setups you can use for your own projects, and several thousand of simulation engineers and designers who are using SimScale as a platform to exchange ideas and collaborate on projects. And yes, to fill these words a little bit with a meaning, let's just take a look at some examples. For example, we have the so-called simulation public simulation project library. And this public library, in the end, if you go on simscale.com, you will see we have in our main menu here on the community, you can click on public projects. And then you can access this thousands of projects. For example, if you're interested in, let's say, valves, you can look for valve-related projects. And import this project with one click to your own workspace for free and use them, for example, to learn a new simulation type or to replace the geometry with your own one and rerun the simulation. And if you just look for valve, you can see how many simulations we have here. And every day new simulations will be added to the library. But SimScale also has a forum, which means in the end how to connect people and content. If you click here now on the forum, you can access our SimScale forum. Every SimScale user who has a SimScale account, which you can create for free, can also access the forum. And the forum, the public project library, and the workspace where you can perform the simulation are strictly integrated. Here, for example, we have different categories. One is project support, where people can ask for help and collaborate together on simulation projects. We have also a category project spotlight, where we create automatically a new topic for every new public project, and where people can discuss these projects and talk about improvements, for example. And we have also a dedicated section for our workshops, and if you go here you can see that we had a lot of workshops this year. And for example, on the Aerospace workshop you will find everything related to our workshop about aerospace industry. But SimScale is even more. We have a lot of video tutorials, a blog where you can find a lot of nice information, and we even have a lot of webinars and workshops. Okay, great. I think I talked enough about SimScale, our product. Basically, you can use it during the workshop for free. And now let's get introduced to our live demo. And today we will talk about the optimization of the aircraft wing. And since most of you, I think, have an engineering background, or at least an aerospace background, I will not talk too much about these fundamentals, but if you have questions, don't ask them. First of all, let's just talk about how a wing is generating lift. And first of all, I have to say something very important. There are a lot of people who talk about misconception aerodynamics, and I will explain the way a wing is working right now with a very easy model, which is, to be honest, not 100% physical true. But there are also other models which have a complete different approach to explain how a wing is generating lift, but no of these models is able to explain it completely. So this is just a model, but it will help us to understand how we can improve the wing. So, first of all, why do we need the wing? What's the role of the wing? An aircraft has a weight, let's say 100 tons, and if you want this aircraft to take off, you need a force which is higher than the weight of the aircraft to have a vertical acceleration. And that's basically what a wing is doing. If we take a look at this, let's say, generic wing profile, every wing has a high pressure and a low pressure side. And just imagine, you have this wing and you have like a uniform airstream coming from the left side. Let me just take my pen from here. And just imagine, first of all, we can assume this air to be made of small layers, infinite small layers, and once these layers, let's just take a look at two layers here, once they hit the leading edge, this part, this edge of the wing, the airflow will be splitted up, and then one part will go over the low pressure side and one over the high pressure side. The low pressure side is also called the longer side, and the high pressure side is a shorter side. If you take a look here, this is longer than this distance. This means that if, and let's assume these two streamlines would meet at the trailing edge, which is physically not true, but it's a good model, then this would mean that the air on this upper side needs to have a higher velocity in order that both streamlines can meet again here at the trailing edge. And there is the law by Bernoulli, which basically say I have a total pressure, let's call it P total, and this total pressure is made of a static pressure, and we have a dynamic component. And this static pressure is our, for example, environment pressure, PO, and the dynamic pressure can be expressed by 1/2 free stream velocity, or velocity at the point, sorry, square, multiplied with the density. And which means if we increase the velocity here, and this total pressure stays constant, our static pressure must drop. And this drop of static pressure creates a pressure difference between the low and high pressure region, which will reduce an overall force which is pushing the air wing up. And that's how a wing is working. So basically we have a low pressure and a high pressure side. The low pressure side is also high velocity side, while the high pressure side is a low velocity side. And now let's just get out of our two-dimensional box and take a look at the three-dimensional wing. In the end, it's the same. We have the streamlines, which will split here, meet here, everything is fine. And here, for example, if we take a look at this cross-section here, through the wing, it will look like here. But just imagine you will take a look here, this area. Here you can see you have high velocity here, a low velocity there, and a high pressure here, a low pressure there. And what will happen now is that, as you know, if we have a pressure gradient, by natural processes, the air will try to get over this gradient. And what will happen is that this high pressure air spills over the wing, and this will generate vortices, which you can see here. And these vortices, let's say it in a very unscientific way, they are destroying our energy. They are transferring our kinetic energy of the airstream into rotational energy. We have a high pressure drop, and this will create additional drag and for sure reduce also the lift. Why is it reducing the lift? Because it will reduce the effective span wide of our wing. And why will it increase the drag? Because the pressure in these vortices will drop, and this will increase the induced drag. As you know, we have two types of drag. We have one part of the drag which is created by the viscous friction between the air and the wall, which is most of the times the smaller fraction of the overall drag, and the main part of the drag is generated because of the pressure drop behind the object. And you can just imagine, if you have a pressure drop behind the wing, that your wing is sucked back. Great, if there are not any questions about these fundamentals, I would like directly to talk with you about simulation and show you how we can investigate an aircraft wing and optimize it. Because as you know, this is a big problem in the aircraft industry. Basically, what they try to do is to use winglets and end plates to avoid this spillover of air on the wing. And then your wing is not looking anymore like this, but maybe like this. And I think you all know these different types of winglets. Okay, great. Then let's proceed. And first of all, what will we do today? Right now, we will simulate the fluid flow around this kind of aircraft wing. And we will analyze based on the drag and lift generated by the wing, but also, for example, if we have a lot of vortices and tip vortices. And I don't want to talk too much about the theory, but I think there are some fundamentals you should know. And first of all, you know what a simulation, but how? How is it working? Okay, basically, whenever you want to do a simulation, you first of all need a CAD model or a computational model of your geometry. And first step every time is so-called pre-processing, which means cleans up the geometry. Just imagine, for example, if you have in your original CAD model, you can have every screw of the wing in the model, but the screw will not have a big effect on the overall flow. Therefore, you can remove them to make the simulation easier. Next step after pre-processing or part of pre-processing is so-called meshing, which means we are dividing up our geometry in small cells, which we use later on for the numerical calculation of the values. And finally, we will visualize and analyze the results. And to make these three steps a little bit more clear, let's just take a look into the fundamentals of CFD. By the way, I saw there was already a question I would like to answer at that point, and it's Andreas who wants to know if it is necessary to have a CAD model when creating a simulation, or if you can create this model inside SimScale, inside a simulation tool. That's a good question. Basically, it depends. Most of the simulation tools are supporting even SimScale to create simple geometrical objects like spheres, planes, or other stuff. But when it comes to make a simulation of a complex shape, it's quite clear that this is not enough to create the model. Therefore, the standard process is that you create a model in a CAD system, and once this model is finished, you can just upload it to SimScale, for example, and set up the simulation there. Okay, great, guys, and I think we can continue if there are no further questions related to that. And next thing I would like to look at is really the fundamental idea of CFD. How are these tools working? And therefore, I would suggest, first of all, that, there's the next question by Robin. Maybe I was a little bit confused, a little bit sorry. Robin wants to know, it's mandatory to use CAD to make the model, or can we also use a program like Inventor? With CAD, I just was talking about this technology. So basically, you can use every CAD tool you want, Inventor, CATIA, Onshape, for example, our partner company, which is offering a free cloud-based CAD, and SimScale is offering various file formats for data exchange between CAD tools and our SimScale platform itself. Okay, great. Robin, did I answer your question, or did it still not really clear for you? Okay, great. Then I think we can... Okay, Ahmed wants to know what's the name of the free CAD software again. And I think I will show you basically that. Just 1 second. Okay, let's switch back to the web browser. Yes, you can see my screen right now, and Onshape is one of our partner companies, and here you can also register for free, and it's a web-based CAD tool. CAD means computer-aided design, and there you can design everything you want, your own aircraft, your own wing, your own landing gear, very easily, and import it directly to SimScale. And Amrit Pals asked if there are any great also about wing theory or where we can learn more practical. Yes, there are some books I can recommend. Let me just take a note, and I will later on post some book recommendations into the SimScale forum. And basically, simulation is a very good way to teach yourself, which I will show you. So later on, you can use the simulation and play around with it and find you out a lot of things on your own. But now let's go further. And first of all, I would like to talk with you how CFD or engineering simulation was invented. And this is just about how fluid flow simulation were invented. And this basically, more than 200 years ago, two very well-known scientists, Navier and Stokes, found out in parallel a formula which is able to describe the motion of a fluid particle. And so this equation, it's more than 200 years old, and we know it's the true equation, is absolutely true, and theoretically you could calculate every flow, every aerodynamical let's say situation based on the equation. But unfortunately, this equation is not solvable. I don't want to go too much in details, but it's an equation, a partial differential equation, and you cannot analytically solve it. But so what can we do right now? And that's a very simple idea. Just imagine you want to simulate the flow, and this gray is our flow field around this body. And you cannot solve this equation analytically. What you do, you solve it numerically, which means you're dividing your fluid domain to very small elements, which we call cells, and then you calculate for every center of one of the cells, you calculate the quantities like pressure, velocity, and temperature. And for sure, as small as the cells are, the more accurate is your simulation result. And because if you have by adapting the local mesh finement, you can optimize the mesh and therefore your simulation results. To give you an example, here, for example, if you just take a look at streamlines, how they would properly look. In this area here, you have nearly no change of the flow variable. Therefore, you can use the coarse mesh. Here, in the near of the body, you will have a higher change of pressure and other stuff. Therefore, it will be smart to use a finer mesh. And basically, there are a lot of regions where you should refine your mesh. For example, in cross sections, in the near of objects, on small features, and around small features, which is for sure a difference. And then I think there's another very important point we should talk about. I hope you all get how simulation is working. So I'm dividing my fluid domain into small regions, and then I use an equation which is describing the motion of flow to calculate locally solutions for this equation. And as you know, we have to adapt our mesh refinement to get the optimum result. And an area where this mesh refinement is very, very, very important is in the near of walls. And therefore, let's do again a step back. Let's think about our wing. And if the flow is, or this airstream is flowing around the wing, we basically think that air is like a complete viscous fluid and we will have no friction. But that's basically not true. If you take a deeper look at the very, very thin layer between the air and the physical wall of your wing, you will see that there is a kind of velocity profile, which means on the wall itself, the velocity is zero. There the air is sticking to the wall. And if you go far away from the wall, you have the free stream velocity. And besides this, or between this, you have this profile, which is describing, in this case, you can see these vectors, or these arrows are describing the flow velocity. So this means a high velocity, a low velocity. And as you can see, this profile changes. And you have a very high change in this boundary layer of velocity. And there you use a special kind of mesh where you have very flat elements to resolve. On the one hand, you have the high gradient in this direction correctly and not wasting cells in this direction where you have a small gradient. And this special type of cells or elements are called layer elements. And as I mentioned, they resolve the directional change of velocity, and they are very necessary. Your simulation results, especially for air wing simulation, will be wrong without this layer elements. And even the height of the layer has an influence on the simulation. But about that we will talk later next week or the week after that. And there is just one rule. Apply this layer on every physical wall, so on every real existing wall, but never apply it on non-physical walls like inlets and outlets. Okay, and now let's talk about one last thing. You may ask yourself how we generate this mesh. And now let's just take a very easy example. Let's imagine you want to mesh instead of a wing this simple car geometry. And first of all, since we want to simulate the flow, we don't need the geometry of the car, but we need the geometry of the flow domain, which is the air around the car. So basically our geometry is the car, and the first step we define a background mesh, which is describing the fluid flow domain. Once we have created this box, we will start to divide it and mesh it into small cells. And after that, this mesh will be refined based on your settings. You can refine the near of edge, you can refine the near of surfaces like here. And once edges and surfaces are refined, you have to define a material point, and then the inner part of the mesh, which is not useful, will be deleted because the flow can only, go through the meshed area. And if we would not remove it, the flow could go inside the car. And once the cells are deleted, we refine the volume, if necessary, around the car, because as I mentioned, you expect the highest changes here in the near of the car. Here you want the highest accuracy of a simulation. And finally, because you have this stairway steps, the mesh is snapped on the surface, and you have a very nice mesh. And the last step is to add layers if necessary, these flat cells, to extrude them from the surface. And that's how we create a mesh with SimScale, or with a so-called snappy hex mesher. Then I would suggest let's just switch to the SimScale platform and create the simulation ourselves. And for this I have prepared a project. By the way, if you don't have a SimScale account, you can just go on simscale.com and create a free new account, which is completely free, and even your access to SimScale is free. And now let's go back here, and you will later on provided with this project. Since Orchan asked me, you don't have to open the SimScale right now. It's okay. You will have 1 week to do it on your own in a tutorial, so it's better to listen. And Rahul also wanted if I can explain Snappy Hex Mesh again. Is there something special you didn't get about Snappy Hex Mesh? Or is it just a general concept, Rahul? Okay, general concept. Okay, then let's go a step back and I will try to explain it again. As you know, our aim is to create a mesh around this car geometry. So we need a mesh of the fluid domain around the car. And in contrast to a lot of other simulation tools, where you need to invest a lot of time for preparing a CAD model, we have a very robust tool called SnapPX Mesh. And this is based on creating a background mesh and in the end morphing this mesh to the geometry you want. So first of all, we create just a block mesh. So just a meshed block, our wind tunnel. And then the mesh is refined based on our settings in the near of edges and around the surfaces of the geometry. Next step is to delete the inner cells because they are not part of a fluid flow region. The mesh will only represent the fluid flow domain and not the car or the inside of the car. And finally, because we have the stairways right now, the mesh is volume refined, snapped to the walls, and if you want, you can add layers. I hope that answered your question, Rahul. Otherwise, we have also a nice description on our documentation page. And Olario, but if you have questions, don't ask them every time. There are no stupid questions, guys, really. And Olario wants to know if he can create his own wing design. Yes, for sure. If you have a tool or if you use Onshape, you can create your own design and import it to SimScale, and I will show you how to do it. But for your homework and for training, we will provide you with ready-to-use simulation project, which already includes the geometry. So let's switch back to SimScale. As you can see, everything here is in my web browser. And this project contains two geometries. And we will now create a simulation of an aircraft wing without a flap, and there's also a geometry included with a flap. A winglet, sorry, not a flap. And first of all, if you want to import your own geometry, you can just click on import and then you can import it from Onshape, or you can upload a CAD model and use different file formats like STEP, IGES, BREP, and STL. And first step, as I mentioned, is to create the mesh. So we will click on this mesh item, and just to introduce general, we have two main menus in SimScale, which will guide you through all steps. Here we have our main menu bar where you can access the three steps: mesh creation, simulation design, and post-processing. And here you can, it's a project tree going up, and following the project tree will be guided to all steps to set up a simulation. So we will start a mesh creation with the mesh, create a new mesh, call it mesh 1, it's okay, and then we have first of all to choose which geometry you want to mesh. And we will mesh the aircraft wing without a winglet. Just click on save, then this tree will be automatically updated. And the next step is to define which kind of meshing operation you want to perform. And as you can see, we have a lot of different meshing types. So we have tetrahedral meshing, which you can use also for other simulation types. We have hexahedral meshing, and there we also have automated meshes where you only have to give something like overall accuracy level you want to achieve. And we also have the possibility to set up the mesh completely manual. Just because a lot of people ask, what means tet mesh, what means hexahedral mesh? The answer is very easy. Tet means that you're dividing your model into tetrahedral elements, and hex means that your elements, your cells, have a hexahedral shape. That's it. And hexahedral elements are better for CFD, therefore we use them. And we will use the parametric one, define everything on our own. First of all, click on save, then everything will be added, and now we can define it step by step. And let's go back to the slide. As I mentioned, first step is describing the background domain. Therefore, we have here the space mesh box, which is the background domain, and by default, our tool will generate a base mesh box. But this base mesh box makes not really sense, because if you would have a wind tunnel like this around your wing, your results would be completely crap. Therefore, we will modify the box, and we can modify it, or this box is defined by 3 opposite points. And we can just modify the points. So let's start. I will just enter the points. So, and this is now our new base match box. And we need a lot of distance between the walls to make sure that there are no interaction between the wing and the walls. You may know or hear about the ground effect, which we covered also at the last workshop 2 months ago. And once it's created, as you know, the next step is to create this background mesh. And now we have to define this initial mesh size. Yes, Paramount asked if the base mesh box is just like a controlled volume. Yes, exactly. The base mesh size is your controlled volume. Absolutely. Well said, Paramount. And next step is to define this base cell size. And therefore we go on this operation tab. And here we can define the resolution by defining number of cells for each direction. So let's 120 use in X direction, 100 in Y direction, and 60 in Z direction. And finally we have to define our material point. This is, I know, for a later stage basically, but that's the point defining which part of the mesh will be kept. So if your material point is here, or here, or here, or here, this part of the mesh will remain. But if your material point is for example here or here, your mesh would be not this mesh, but like would look like this. Okay. Okay, now let's go back, and here you can also visualize this material point. It's right now here, and this is too much in the near of the wing, so I will just move it a little bit in X direction, and now it should be fine. And I will move it a little bit more in that direction just to make sure that it's not intersecting with the symmetry plane. And a good trick is to use random numbers, not integer numbers, because that can sometimes create problem. If this meshing point, for example, is exactly, material point is exactly here, this can create problems, and therefore I would just put it like here, or here, or here. Okay, now we have defined our base mesh box completely, so step 1 is done. And our next step is we have different refinements. So first of all, I will define a surface refinement and cylinder refinements. And there's a question by several questions. First question by Mario. I think he wants to know if the box needs to be that big size. Basically, Mario, yes, that is absolutely mandatory. And let me explain you why. We want to simulate the effect or the aerodynamic of the wing only. But since we are using a numerical method and we work on a computer, we need a control volume. And our main aim is to avoid any interaction between the main volume and the wing. And if this wing would be too much in the near of the wall, then it could happen that you have an interaction. Let me give you a very easy example. Just imagine this is your float channel, and this is your wing. It's a very extreme example. Then your streamlines would look like this and be influenced by your box. And that's the reason why we use a larger size. By the way, because Erimantis asked, all settings on SimScale have to be defined in standard units. So this is meter, kilogram, newton, etc. And Mark wants to know how we can properly define the number of cells in each direction. Do you know, Mark, how to define them in SimScale, or how to find out about the right cell size? And okay, Mark, you can just define your size, your initial cell size, base mesh size here in this menu on the cells in X, Y in the direction. If your bounding box has a length of 100 meter and you choose 100 cells, then the initial length will be 1 meter. And the right size, it's, to be honest, based for example also for sure on experience, but basically I would say for a wing you should have a very fine mesh, about several centimeters maximum size at the wing surface, and maybe 1 or maximum 2 meter cell size far away from the wing. Okay, but if you have any more questions, just write them down and let's continue, and I will try to answer them later on. So we have defined, and since we want to do only region refinements, as described here, we have to define some refinement zones, and therefore we will just create, we can create a box, a cylinder as well. We'll just create a cylinder or several cylinders. So example 1 for the outer region around the wing, and we can define them based on a reference point and axis and radius. So this, for example, is a refinement box I created around the wing. I will now create an additional one for the inner region. I will use a slightly different reference point, and for sure another radius. So we have now 2 refinement cylinders. And finally, I will add 2 refinement cylinders to solve this high gradient area at the wingtip. So let's call it wing tip region 1. Here, and I will create a second one at this point. Here, I hope you can see it. It's this small one. Okay, and now we will just add the refinements, and then we will be able to create the mesh. And we will start first of all with a so-called surface refinement. And we have this geometry is made out of 3 surfaces. One surface 1, 2 and 3. And as you can see, this is surface 1, surface, sorry, this is, we have a surface here for the profile, we have a surface for the very small leading edge, and we have a surface for the whole wing itself. And we will add now 2 surface refinements. The first surface refinement, let's call it surface wings, because it's a surface refinement and will be applied to this 2 wings, but not on the leading edge. And there we define a minimum level between mesh level between 6 and 7. What does it mean? This is very important to understand. At SnapPX mesh, you don't want to define the mesh size based on length, but based on level. And level, increase of 1 level cell size is equivalent to split the cell. So to make it a little bit more vivid, this is level 0. This is splitted 1 time, level 1. And if you would, here we have level 2, which also means that increasing the level by 1 will make you have 3 times more elements. Since I was against several times, yes, the session will be recorded just to let you know mode. Okay. And level 6 to 7 means that automatically the tool will choose the optimum mesh size between 6 and 7, and increase the refinement of the cells, or increase the cell density on the surface here. Then we will create additional surface refinement. Let's call it surface edges. Here we want to have a uniform mesh size of 9, which is several times finer, and we will only apply it on this small leading edge face of the wing. Great, then only thing which is missing is we need additional region refinements to define them, because right now we only defined the refinement box but not the size. So just select, for example, the outer region and define a global level for this whole volume. Apply it, and then we will create additional region refinement for the inner region and the wingtip. There we want to have a mesh size of 3 also. And finally, we want a much finer mesh in this region 3. Great. And finally, we'll just add 2 kinds of refinements, edge refinement. This will, and here edges will be extracted based on a feature angle, so of which we can define, and then we can also define which level we want to have on the given distance from this edge. So exactly on this edge, on all edges, we will have a refinement level of 6. And last but not least, we will add the layers. So we choose the type layer addition, apply it to all faces, on non-physical faces, and then we can define how many layers we want. We want to have 4 layers. We want to have a growth ratio of the layers of 1.65. We want a fine layer thickness of 0.3 and a minimum thickness of 1/1000. And these values are relative and will be applied to the local mesh size of the face. And now our meshing is completely defined. The final thing we have to do is to start this meshing process itself by clicking here on the Start Mesh Operation button. Now this operation will be performed in our cloud, which is much faster. And just maybe one thing, you can for sure also cancel every time you want a meshing project, and you can also choose the number of computing cores you want to use. Since the meshing, even with 30 cores, takes a little bit of time, we have, or I have prepared already a simulation project which includes a finalized mesh. So let's open this project. By the way, there's a question by Mark again. He wants if it's possible to do a smart meshing which would automatically adapt to the shape of the studied object. Yes, this is possible. We even have this kind of mesh available. And this measure is, let me just show it you, is called the hex dominant automatic measure. But for sure the result is not as good as when do it manually, but for a lot of application it's enough. And we're also working on some very nice features which will automate meshing, even for parametric meshing, more and more in the future. So this is how our mesh looks after it's computed. You will be notified by email or at least in your workspace based on your settings when your mesh is finished. And if we, for example, now take a look, you can see here, for example, that this mesh has 5.6 million cells. Which is a lot. That's the next question by James. If we are not sure about what kind of meshing do on the zone of the object, what would you recommend us? Jamie, I have not got your question completely. Can you maybe describe it a little more? And I will just proceed with my presentation, and next time I have a break, I will just answer your question. Okay, now let's take a final look, and we can even take now a look inside our mesh. For example, we can hide these outer faces, and then here take a look. And as you see, this mesh was really depthed here in the near of this edge you have much finer elements. And what I also like is, let's take a look at this symmetric wall. And if we now zoom here, sorry, like this, you can, for example, see how layers were generated here. Okay, great, then meshing is finished. Let's do a quick wrap-up. I showed you how to create or open a project and how you can theoretically import your own geometries. We talked about hex-node meshing, parametric one, which means we talked about the theory, why do we need meshing, and how the snappy hex mesh is working, and we talked about layer elements, which are very important to resolve the high velocity gradients in the near of the wall properly. What we cannot talk too much about today is CAD cleaning and repair. So how can I repair a CAD model? For example, make it watertight, which is necessary for fluid flow simulation. And we could also talk more about manual meshing setting. But with this knowledge, and as I mentioned, you will do this yourself as a homework. You will get a tutorial, and I think there you will gain a lot of additional understatement. Okay. Then let's switch back to our platform. In the meantime, I just would like to answer some questions. First of all, okay, Jamie, okay. So you want to know when you should use hex elements and when you should use tetrahedral elements, right, Jamie? Okay, as I mentioned, basically you can use both elements for fluid flow simulation, but generally speaking, hexahedral mesher, hex mesh, will give you better results with the same number of cells. And it can also explain you exactly why. Just let me switch back to my slide. Just imagine if you would use tetrahedral cells, you would have the double. You would have the double amount of cells. For sure, that means you would also have two values. But generally speaking, tet meshing is easier because it's easier to approximate with the tetrahedral elements a complex shape, but the result quality for numerical and mathematical reasons of a hex element is better. Therefore, I suggest to use hex element for CFD all the time. Okay, the next question is by Stefan from Super Aero France. Does the software automatically recognize the presence of the object and does not go through the object? Stefan, I think you are talking about this material point thing, right? So yes, based on the material point, and this is what I wanted to show you again here, right now the flow would go through the car, inside the car, and based on the material point, which must be outside of this geometry, for example here, the inner part of the mesh is going to be deleted, and that will make sure that no flow is going inside the object. So Stefan, I hope this answers your question. And Rahul wants to know, how does the material point work to delete cells? This is really very complex. It's about the code. Therefore, I would not like to talk so much about it, but I can, if you want, Rahul, just send me an email and I will send you a paper describing how it's working. But a lot of hard coding stuff. And okay, I got it. You want to know how the choice of the point changes the deletion of cells. Then one last time. If your point, you can see it, I think, here. This is the geometry of your car, right? Here. And if the material point, now we have, like, say, like two meshes. We have one mesh, I make it red, the inner mesh, and we have like the outer mesh, which is outside, ending here. And based on where your material point is, the tool will decide which part of the mesh it should delete. If your material point is here, then the inner part of the mesh will be deleted, and if it's inside, the other way around. I hope you got it, Rahul. Okay, now let's go back and let's set up our simulation right now. So, because we're also running out of time. Right, so as you see, we can even take a look at the mesh. The next step is to set up the actual simulation. And therefore, we go on the Simulation Designer tab and click on Create a new simulation. And then we have to decide what we want to simulate. I will want to do aerodynamic simulation, so I'll choose fluid dynamics. And we will do an incompressible simulation, since it means we assume that the density of the fluid will not change. And this depends on the speed. If you are on the near of speed of sound, your flow becomes compressible, and which will make your simulation a little bit more complex. If you're interested in that, we've covered that topic at our old workshop, Aerospace Workshop 1. And you can still access everything you need. Then we have to define three things. First of all, we ask for the turbulence model. And flow can be turbulent or laminar. And if it's laminar, we choose laminar. And if we want to simulate turbulence, we have different options. First of all, to simulate turbulence completely, most of the people think turbulence are vortices, and that's basically not wrong. So you can see here these vortices. And if you want to resolve this very small scales of the vortices, it would take too much time. Therefore, we will use a model to let's say, interpolate turbulence. And to be honest, K omega SST is the best one for all aerospace applications, so we should use this one. Then we are asked if we want to have a steady state result or transient result. We want steady state, and based on this, we will use the so-called simple solver. Clicking on Save will update your project tree. First of all, we have to choose which mesh we want to use for a simulation. The mesh will then be added to the 3D viewer here. And the next step is to define, first of all, which is the material of, or which is the fluid. What kind of material is it? Therefore, we go on Material, click on Add New Material, and now we have two very good options. One option is to define your material just based on the kinematic viscosity, but so you can use like your own materials, but you can also access our material library, which includes several materials, and you can import them with one click and add them. And now we define that the fluid around the wing is air and not water or oil. Next step is to define so-called initial conditions. I don't want to get too deep into what is initial boundary condition, but basically imagine the following. You know we cannot solve this Navier-Stokes equation analytically, therefore we do it numerically. And it's done iteratively. So we take an initial solution, and every time the solution becomes more and more accurate. But since we need initial solution, we have to define it, and that's what we do with initial conditions. And here, first of all, I will define initial pressure. So this is the value for the whole mesh at the beginning of simulation. Will be pressure of about 1 bar. Basically, you can also use 0 bar, but it's just a pressure difference. But then you have to stick to this 1000 bar. For the velocity, I have, since I want to have like a small angle of attack on this wing, I will, as you see right now, it's like right now it has no angle of attack, but since I want to have angle of attack of about 10 degree, instead of having a flow in this direction, I will have a flow from this direction, for example. And therefore, I define two components. I want an overall fluid velocity of 70 meters per second, and this is, if you calculate the component based on 10 degrees, means 86.94 meters per second in x direction and 12.16 meters in y direction, and in that direction there's no component. For k and omega, we can just use these default values. These are values which are used to compute or describe the turbulence of the airstream, and we don't have to modify. The next step is much more important, the so-called boundary conditions that are describing how our model is interacting with the environment. And first of all, let's start with the inlet, which is a little bit more complex this time. This is this, and we will First of all, since we have this angle of attack, we cannot assume this or that wall as a wall. They have to be dependent on the flow, an inlet, an outlet, or a wall. To give you just a very simple example, once again, sorry, if we would have this normal flow, we would make this walls closed. But since we have this angle of attack, and if you think about it like this, theoretically here air had to leave and here we need air to enter with the angle. And therefore, instead putting an inlet here and an outlet there, we use this dedicated kind of boundary condition, which I will show you. But don't worry if it's confusing you. We also described the boundary condition in the tutorial, so let's call it inlet outlet, because it's both inlet and outlet. And the type is custom. It's very important. And for the velocity, we use the boundary type inlet outlet. And again, defining here and that's very important. For the pressure, we choose zero gradient, which means we don't know the value there at this surface, but we know that the value will not change. It's a constant value. And for turbulence, we will just apply fixed values, the same ones we used for the initial conditions. So just enter here 0.0037 and 3.375. And we will apply it to a lot of phases. To this phase, basically we will apply it to to this phase, to this phase, to this phase, and to this phase. Done. Next boundary condition is a little bit easier. The symmetry. Yes. There we just choose this surface, type symmetry, and that's it. And our final boundary condition, last one, is the wing itself. Or no, first of all, let's call it slip wall. Since we don't want that this wall is interacting with the flow, we make it the wall but a slip wall, which means the flow is not interacting with the wall. And finally, we will make a wall for the wing itself and choose the wing faces. Great. Well, we are nearly done. And there's basically just some small things which we have to modify. First of all, let me just answer some questions. First of all, Vakul wants to know, do we have options of using Piezo solver? Yes, you have. I will show it to you later on. SimScale is based on OpenFOAM. We are also contributing ourselves a lot of code to the foam community, and basically you can even upload a foam case. Pilo wants to know if we can only simulate comms from infinite, or if we can also simulate sources and drains. Pilo, that's possible, but it depends on the kind of boundary condition you want to use. Oh, question of my old friend Alex. He wants to know, how did I assign the values of the properties in the inlet, outlet of the boundary condition? Okay, let me show it to you again. You choose boundary condition type custom, and then, maybe this is easier to understand, you have to define your custom boundary condition for velocity, for pressure, for turbulent kinetic energy, and omega. Well, now the next thing, as this simulation tools are based on numerical solving. Therefore, there are some numerical settings which we can optimize in order to reduce the computational effort. And to be honest, I will just change this value to show you, but Basically, don't think too much about it. You will learn the meaning of the value by experience over the time. Basically, the relaxation factors, these ones say how aggressive or let's say conservative the solver should try to solve the equations. And I will just change them a little bit. I will increase them, so to make the simulation, decrease them to make the simulation faster. Then I will add a non-orthogonal corrector. You can imagine the mesh can be non-orthogonal, so it can be like banded, and this can create numerical problems. And finally, I defined a pressure reference value again of 10 E5 to make the simulation more stable. Then I will change some other stuff. So first of all, I will change the solvers. These solvers are used to, let's solve the equation for pressure, velocity, and turbulence quantities. And first of all, I will change this. I will keep this GAMG solver for pressure and change the tolerance to 0.005. This tolerance is basically the tolerance which is used to stop the simulation when it's converged. We will see that later on. And I will change this one to smooth solvers with default settings. And finally, I will change the numerical schemes to calculate gradients, etc. we need. And for pressure and velocity, I will use this cell-limited Gauss linear schemes. For the Laplacian schemes, I will use Gauss limited corrected. And finally, for the divergence schemes, I will use bounded Gauss upwind. Just save it. And now we are nearly finished. We just have to define our simulation control. So we have to define how many iterations we want to run. Pablo has a question I will answer it right now. So we want 0 to 2000 with a time step of 1 means we will have 2000 iterations, and every iteration here we will increase the quality for simulation. We just want to save the final simulation result, use 32 cores, and we want to have a maximum runtime of 90,000 seconds. So after 90,000 seconds, simulation will be stopped, even if not 2000 iterations were performed. And we will not use potential form in this case, which is to assume flow. And the final step is to add force and moments, so we can calculate during the simulation the forces on the wing. And now we're finished. We can check the simulation, create a new run, and start it. Okay, great. Then let me do just a quick wrap up and answer your questions. First of all, Pablo wants to know, while doing the homework, will be the condition parameter specified in the task, or do we have to estimate them? No, Pablo, you will get a step-by-step tutorial. Everything is described. But for sure, we would like if you play around with the setup and try things yourself. And the next question is by Brendan. Are there any settings where a slight mistake can be catastrophic for simulation time? Things where if I accidentally type 6 instead of 5 will make it take 5 times so long. Yes, for sure. For example, basically there's a lot of intelligence that's inside SimScale. So, for example, if you define, let's say, your start value is higher than your end value, then you will automatically get warned. Basically, the only thing you can really mess up in the simulation is mainly using wrong boundary condition making a simulation crash, or using too less CPUs. It can also be a problem. Okay, Alex has some questions related to the boundary condition. Very easy. Let's talk about it again. I think you're talking about these numbers, right, Alex, about the values for the inlet velocity? Yes, okay. As I mentioned, I want to have an angle of attack. Right now, my angle of attack, which is the angle between, so this angle, again, sorry, this angle is 0. And now, since to have angle of attack, I can also change the direction of my flow, and I won't have not this flow direction, but like this one, with the angle of 10 degrees to the wing. And then I just calculate, I just take a triangle in the end. Then I have a x and a y component and a resulting component, and then based on alpha, I can calculate using cosinus and sinus the components. So if you calculate the magnitude of this component in 70 meters per second. And there's some question related to the homework. Let's just talk about it in 5 minutes. Okay, great, guys. Basically, just because some people ask, I think the homework will take you about half an hour to 45 minutes from our experience. But I will show you your exact homework just in some seconds. Alex, I hope this answered your question. Okay, then let's do a quick wrap up, my friends. Yes, I showed you how to generally create a simulation setup, how to assign the mesh, define the materials, and we talked about initial conditions, boundary conditions, especially how to define velocity in the boundary conditions, and we started the simulation. There are some things where you should learn more about, but this is nothing you have to learn today or tomorrow. This is something knowledge you will gain by experience. And also by maybe some research. And therefore, advanced topics we have not talked too much about right now is turbulence, numerical solver sectioning, and advanced solver controls. Okay, then there is, before we take a look at the next step, post-processing, there's just a question by Quentin, and he would like to know why we need this cylinder, and I will try to explain it to you. If you take a look at the mesh here, you can see that we have a much finer mesh here and here. And we defined this refinement with this cylinder. And we told it, in the end, we told the meshing tool here, refine all cells inside this cylinder to a level of 2. And therefore we use the cylinder to refine the volume mesh. I hope that answered your question. So, and right now we could theoretically start a simulation, since this will take several hours. Till it's completed, I will just switch to this simulation where I already have the finished simulation. Guys, don't worry. In 5 minutes, I will show you your homework and how you will find, or where you will find the resources. So let's go to the post processor, and once the simulation is finished, by the way, you will get notified, and then this progress bar will come to 100%. And first thing what you can see is this so-called convergence plot. And here you see the average error for pressure, the 3 velocity components K and omega versus the simulation iterations. And you can see that all this error, the error got done all the time, and in the end the highest error I have is less than E-3. And we can even, if we go to post processor, take a look at how the force developed against the iteration. You can also see that after, let's say, 1,300 iterations, all values became stable, which means our simulation is converged and is physically correct. And you can also take for sure a look at the 3D simulation results, clicking at solution fields item in the project tree of the post processor. And this will take now maybe 1 minute to load the data, because it's really a big mesh, but don't worry, it will take much longer on a local computer. And once it's loaded, since everything is in the cloud, you will never have problems with loss of data, stuff like that. Everything will be saved automatically. And right now, let's do just some basic result analyzers. And you can play around with it during your homework. So, it will take some time, sorry guys. By the way, there's some more question I can answer in the meantime. Just write them down. Great, and now our simulation is there. And first of all, let me explain you the main structure. We have this post-processing tree, and right now we have loaded the internal mesh, as you can see here, of the simulation. So all the parts of the mesh except the surface parts. And here you can change the simulation step, so we are at the latest step right now, and this you can use to change what you want to be represented. First of all, I will add the solution field, the simulation, a second time to the viewer. You may think that's stupid, but you will see why. Because I will hide now the internal mesh completely. and import only the surface of the wing so that I can visualize both the flow field as well as the surface of the wing. And sorry, this can take some time, especially when a lot of people are active on the platform or your internet connection is a little bit used. But for smaller simulation, it's much faster. And you can also download the simulation results to play around with them on a local post-processor. And we will now calculate first of all here, I will here choose these two faces instead of the internal mesh. Alberto wants to know if the boundary box is too big, but no, it's the right size. Basically, your books cannot be too, your bounding box cannot really be too big. Since several people asked, I will send you some book recommendations in the next days. Okay, now we can start. First of all, so this is our wing. Let's zoom. And everything is right now blue, which makes sense because the velocity on the wing is 0. So let's change from velocity to pressure. And now you can see the legend also, and you can see we have here our low pressure side, our high pressure side, and we can even create, for example, a slice through the domain to have a better visualization. Sorry guys, just 1 second. I will change the origin to 5 meters, and I will also change the normal to following value. And then this will create a cut through my wing. Now let's hide the wing surface and take a deeper look. Okay. So this is our wing, and you can really see here the high pressure region, the low pressure region. If we take a look at the velocity, then you can for sure also rescale. Then you see how, I'll rescale it again. You can really see that the air is accelerated here, and you can even see the boundary layer if you zoom. Let's change the representation so it's edge, and then here you can really see the boundary layer. Here is this blue area, small blue line here. Great, and another nice thing we can do, for example, is adding additional filter to the slice. And we can also create streamlines, for example, and other nice things. So and the good thing is you can switch also from everything you want. If you, for example, like Albert asked, want to calculate CL and CP, you can just here take the force, you can see the force here. example, y direction, we have a pressure force of 1680 Newton and a viscous force of 1100, 16,000 and 1,100, sorry, and you can just take these forces to calculate the CL and CD manually. Okay, and there's a question by Enrique, and Enrique wants to know if there are any dedicated requirements, computer requirements to be able to run SimScale. And first of all, since SimScale is browser-based, you don't need to install it, and we also have no official requirements, because in the end all the calculations are done independently from your computer in the cloud. Therefore, I would say a standard computer, even a Chromebook, a netbook, is enough to access SimScale. What I would suggest you should have is at least a high enough resolution for your screen, and a mouse, a computer mouse is good. Okay, then I think we're really out of time, so I would like to show you so much more post-processing, but I think you will do it yourself in the tutorial, so that should be fine. Then finally, yes. Thank you very much for attending, and right now let's discuss your homework assignment, and then we can discuss about your last questions. So your homework will be to create such a simulation yourself and analyze it, and for both geometries, for a wing without winglet and a wing with a winglet, you can see here, and to compare the results. On simscale.com/aerospace workshop, you will find everything you need there, or you can even, so I will add tomorrow in the morning all the resources here, but you can already find them right now on the forum in the category, this category here, SimScale workshops, aerospace workshop. There is workshop 2, homework 1, optimization of a wing. Just click here. Here we will also put tomorrow about lunchtime the recording of the session. Here you can also will find from tomorrow this homework submission form. Here you can import the project including the geometry, and here you have your step-by-step tutorial explaining every step. So really everything you need you will be provided with. And yes, I'm really looking forward to your work. And if you have question ideas, if you simulate every something on your own, or if you need help with your simulation, just write under this post in the forum, and our SimScale engineering team will help you to get everyone's simulation running. Okay, great. It was such a big pleasure, guys. Thank you so much. If there are any more questions, just ask them right now, and just write them there. And if you have, maybe you get a question tomorrow, you can write them in the forum or reach out to me. Just one last thing from my side. If you have something like a problem with simulation, please write it first into the forum, because if we answer it there, maybe other people can also read it later on, which have the same problem. Okay, let me answer now the last question. First of all, Stefan wants to know what is the right size for the box, and to avoid interaction. A very good rule is you should this 10-15 rule that says you should have in front 5 to 10 times distance of the object, behind 10 to 15 times, up and down 5 to 10 times. That's a good, but it depends on the flow. Or if I would just play around, you will see if there is interaction. Yes, Rodrigo, I will post the books I suggest under the forum. That last question is by Anton. Is the internet connection required to run the simulation? No, it's not required. Once you start the simulation, you can just close your laptop, computer, and even go to another computer, and the simulation will be proceeded in the cloud, and you can exit from everywhere you want. Okay, guys, if you have some more questions, just write in the forum. Thank you very much for being with us. I hope to see you all next week. Thanks again to Eurovia for helping us to organize this workshop. Thank you very, very much. It was a pleasure for me. I wish you already a nice weekend, and see you next week. Bye.